Bismillahirrahmanirrahim. Let's start the next lecture on heat and mass transfer. In fact, we are going to start chapter number 6, the title of which is Introduction to Convection. However, we had a very good introduction to convection in chapter number 1. So it is highly recommended, rather it is essential that you first go over that particular session that we had on convection while we were on chapter number 1, because the things that were covered over there would be required over here, and since they have been covered in a lot of detail, so they would not again be discussed in details over here. Rather, the things that are ahead of that prior discussion will be discussed in this particular chapter. So we will start with the classification of fluid flows. These are some of the topics that we would be covering inshallah ta'ala in this chapter, and then we will cover the boundary layer theory. The boundary layer theory has already been discussed in a lot detail in that previous lecture. So we would not be going over velocity and thermal boundary layers in a lot detail over here because they have already been covered before. We will be going over some dimensionless numbers. You would already be well aware of the very famous Reynolds number. However, we will be covering Nusselt number and Prandtl number as well. We will then go over local and average convection coefficients, convection heat transfer coefficients, and then we will cover the three famous equations, conservation of mass, momentum and energy. We will then discuss the boundary layer similarity. We will see what is meant by boundary layer similarity and how do we normalize the boundary layer equations. And we will also go over this functional form of solutions. We will see what does it mean, what is meant by the functional form of the solutions, what is the use of those functional forms of solutions. And in the last, we will go over boundary layer analogies. We will discuss two types of analogies. One is called the Reynolds analogy. The other one is what we call the modified Reynolds or Chilton-Colburn analogy. So those are the topics that we will inshallah cover in this particular chapter. So over here we are starting with the basic phenomena of convection. Kindly refer to the previous discussion on convection. But summarizingly, convection will take place when a fluid would move over a solid surface. So it is a mechanism of heat transfer through a fluid in the presence of fluid bulk motion. Right? So there should be a bulk motion. What is meant by bulk motion, that has already been covered in that previous discussion. There are various classifications of convection. There are the convection may be classified as either forced or natural. So natural convection is that type of convection in which we do not use any external means to make the fluid flow over the surface. So if we are not making any external source such as a fan or a blower, so that would be natural convection. However, if we are using a fan or a blower or any other type of device to make the fluid flow rapidly with higher velocities over the surface, so then that case would be termed as forced convection. External and internal convection, if the fluid is flowing over a plate or outside a pipe, so that would be termed as external convection. If it is flowing through a pipe, so then it would be termed as internal convection. So chapter 8 deals with internal convection, where the fluid would be flowing through a pipe. And these are the things that we have already discussed previously while we were on chapter number 1. That convection heat transfer is not a fluid property. Convection heat transfer coefficient is not a material's property, because it depends upon so many parameters, and we had discussed those parameters, the dependency of convection heat transfer coefficient on those parameters over there. The fluid flow may also be classified as either viscous or inviscid. So inviscid flow would be sort of an idealized flow. Idealized flow of zero viscosity fluids. So if we are neglecting the velocity, so then that flow may be termed as inviscid flow, or if it is very small, so small that it can be neglected. However, there would always be friction between the layers of the fluids. So in reality, the flows would be viscous. However, sometimes they are approximated. They are assumed as inviscid flows to make some simplifications and make the things easier. Internal versus external flow has already been discussed. Compressible versus incompressible flow. See, it depends upon the density. If the density of the fluid remains constant, then those liquids or fluids would be termed as incompressible substances. In fact, the densities of the liquids remain constant up to a good extent. Up to a good extent, we need very high pressures to change the densities of the liquids. So therefore, liquids are usually classified as incompressible substances. However, when we come on to the gases, so gases are highly compressible because they have got a lot more space between their molecules or atoms. So gas flows can be treated as incompressible if the density changes are under about 5%, and this will usually be the case if the fluid velocity is less than 30% of the velocity of the sound in that gas. Means if Mach number is less than 0.3. So if this is the case, then the flow of the gases may also be termed as incompressible. However, if this is not the case, if the density changes are more than 5%, or which would happen if the flow velocities are more than 30% of the velocity of the sound in that gas, so then of course the gases would be termed as compressible. This is a very famous classification when we come on to the fluid flows, laminar versus turbulent, and those terms would not be new for you. You would have gone over, or you would have learned those terms in fluid mechanics. Laminar flow, this is how a laminar flow would look like. This is how a laminar flow would look like. It is very smooth, and this chaotic flow, which is not very smooth, is termed as turbulent. Over here again, this is laminar, and the bottom one is turbulent. So some flows are smooth and orderly, while others are rather chaotic. So the highly ordered fluid motion, which is characterized by smooth streamlines, is called laminar flow, whereas the other one is called the turbulent flow. The flow of low viscosity fluids such as air at high velocities is typically turbulent. Right? Any flow may be turbulent. That would of course depend upon various parameters such as the velocity, such as the viscosity. We will see how we can determine whether the flow is laminar or turbulent. Of course, you would probably know it from your prior knowledge of fluid mechanics that we usually calculate the Reynolds number, and the Reynolds number, the value of the Reynolds number can tell us whether the fluid flow over a particular plate or through a pipe is laminar or turbulent, depending upon what values do we get. Again, over here it's a schematic, it's a visualization of how a turbulent flow looks like and how a laminar flow looks like. So you can see that the streamlines are very highly ordered. So that type of flow is called laminar flow. But if the flow is getting separated, as is shown over here, and it is no longer highly orderly, rather it is chaotic, so then that type of flow is called turbulent flow. This type of flow would be termed as turbulent flow. Again, the flow may be steady or it may be transient, just like the heat transfer may be steady or transient. And if the fluid properties, if the properties are changing with respect to time at a particular point, so then the flow would be termed as transient. However, if the properties at a particular location are constant, they are not changing with respect to time, so then that flow would be termed as steady. And just like the heat transfer may be 1, 2 or 3 dimensional, as we had seen in chapter number 2, especially while we were deriving the heat diffusion equations and we were discussing the 3 coordinate systems. In Cartesian we had 3 dimensions, x, y and z. Similarly in cylindrical we had 3 dimensions, and in spherical we also had 3 dimensions. So in a similar manner the fluid flow may be 1 dimensional or 2 dimensional or 3 dimensional, depending upon the components in those particular directions, x, y, z, r, z and angle, and in a spherical r and 2 angles, theta and phi. Over here we are starting with the velocity boundary layer. As discussed before, there are 2 boundary layers. In fact, we would be coming across 3 boundary layers: the velocity boundary layer, the thermal boundary layer and the concentration boundary layer. But the concentration boundary layer will be dealt with in the later chapter of mass transfer. So for now we would be restricting ourselves to velocity boundary layer and the thermal boundary layer. So again I would request you to refer to that previous lecture on having a good understanding of velocity boundary layer, because over there I had explained the velocity boundary layer and the thermal boundary layer in a lot of detail. However, just for the sake of summarizing the things, whenever a fluid flows over a surface, over here we can see that the fluid is flowing over this surface. So there would be a region, there would be a particular region in which the effects of the plate will be felt. And how the effects of the plate will be felt? The fluid which is near the plate would be having lower velocities, and the fluid which is far from the plate would be having velocity of u infinity, where u infinity was the free stream velocity. So we would have this particular region where the effects of the plate will be felt, and that particular region is called the boundary layer. If we are, and delta is used to represent the thickness of the boundary layer at any particular location. Of course you can see that the thickness of the boundary layer grows with x, it increases with x. And we also had discussed previously that we had discussed a particular condition which is called the no slip condition. And the concept behind no slip condition was that the fluid consists of a lot of in fact infinite number of layers, and the very first layer of the fluid, which will be in direct contact with the surface of this object, would be having the same velocity as that of the object. So therefore the relative velocity between the two would be 0, and then the velocity of the second layer would be a little bit more, and the third velocity would be even more. And therefore over here we can see the velocity profile, that the velocity would increase as we go far away from the plate, and then there would come a time where the velocity would be the same as the free stream velocity of u infinity. So velocity boundary layer, the boundary of the velocity boundary layer would be the point where the velocity is approximately 99% of u infinity, because after 99% it would be 100% of u infinity. So this region within which the velocity would vary from 0 to 99% of u infinity is termed as the velocity boundary layer. And similarly over here this is again not a new expression for you. it is for the shear stress, and it is given as mu dou u by dou y. It is the simplest of the equations that you would have seen in fluid mechanics. Over here we are given another expression in which the shear stress, how over here the tau s is representing the shear stress, mu is the viscosity, u is the velocity, dou u by dou y is the change in velocity with y. So over here we are bringing another term which is the CF, and CF is called the friction coefficient, and of course it is dimensionless. And over here CF is tau s is half rho v square times the coefficient of friction, where half rho v square would have the same units as that of a force, and upon its multiplication with a dimensionless term will give us the units of shear stress as the regular units of shear stress. So if we say that tau is force per unit area, of course it would be per unit, this would be in terms of per unit area, rho v square. So if we keep the force over here, if we write this tau as force per unit area, and then if we take the area onto the right hand side, so therefore CF would remain CF, half rho v square remains half rho v square, and then the area would come over here. So these are the expressions that we might be using while solving the problems. However, they are very simple equations. Tau s is half rho v square times the coefficient of friction, and tau can be written as force per unit area. Ff means frictional force, and tau s means shear stress over that surface, between the surface and the fluid. The next boundary layer, as I have just told you, is the thermal boundary layer, and thermal boundary layer would exist due to the difference in the temperature, due to the difference in the temperatures between the fluid and the plate. So of course, if of course the temperature of the fluid would be and the temperature of the surface would be different, and therefore the heat transfer will take place between the surface and the fluid. So if Ts is greater than T infinity, if for example if Ts is greater than T infinity, so this temperature profile will be made in this manner. I have already explained it in a lot of detail in that previous lecture. So Ts minus T infinity would be large near the surface if Ts is greater than T infinity, and as we move away from the plate, the layers of the fluid would be approaching T infinity, would start approaching T infinity, would be having temperatures closer to T infinity. So therefore the difference between Ts and T infinity will keep on reducing unless the temperature of the fluid becomes the same as T infinity. So this is that region where the effects of the temperature of the fluid are being felt, and that is why this region would be termed as thermal boundary layer, thermal boundary layer thickness is given as that value of y for which this ratio is 99%, and you can see over here that if over here Ts is the temperature of the surface of this object, T infinity is the free stream temperature of the fluid, and T is the temperature of along y. So if as we move in y direction away from the surface, so therefore T will keep on changing. You can see over here T will keep on changing. So if we move far away from this plate, and if we move closer to T infinity, so if this T becomes almost the same as T infinity, so then this ratio will almost become equal to 1. So this is what this ratio is about, and the heat will be transferred from the surface to the very first layer of fluid, which is in direct contact with the surface, would be via pure conduction, because the relative velocity between the two means between the surface and the first layer of fluid, would be 0, and therefore the heat will be transferred via pure conduction from the surface to the first layer of fluid if Ts is greater than T infinity. So therefore Qs heat flux can be written as minus K of fluid, Kf means K of fluid, times dava T by dava Y at Y is equal to 0. And then the same heat will be transferred to the second layer, and from the second layer the heat will be transferred to the third layer, and so on, and in this manner heat will be transferred from the surface to the whole fluid. Over there we know that the Newton's law of cooling is the expression for convection heat transfer, in which Q is given as HA delta T, or if we bring area under the denominator of Q, so that would become the heat flux, and then the right hand side would be written without area. So if we then compare this expression with this one, if we compare these two expressions, because the heat that will be transferred initially from the surface to the first layer of the fluid will further be transferred to the subsequent layers via convection, right, if the system is working under steady state conditions. So then if we compare these two, so then we can write this expression of H, that H would be equal to minus K times dava T by dava Y over this Ts minus T infinity. So this is a useful expression for H. Again, I would emphasize you to refer to the previous lecture on convection, which we had undergone while we were on chapter number 1. Over there we had discussed convection in a lot of detail, so kindly refer to that for in-depth knowledge and for revision. Now continuing the thermal boundary layer, this page is in fact very important as it discusses some of very useful facts that are being mentioned in this diagram. See, it says that since Ts minus T infinity is a constant quantity in HA Ts minus T infinity, and this quantity is independent of x, because Tx would remain constant as we move along the length of the plate, and in addition to that T infinity would also remain constant as we move along the length of the plate, while delta T, the thickness of the thermal boundary layer, increases with increasing x. We can see that it increases with increasing x due to the reason that the fluid comes in with full potential at the start of the plate, and therefore it takes time for the boundary layer to grow along with the length of the plate. So then it says that the temperature gradients in the boundary layer must decrease with increasing x. This is very important point. The temperature gradients in the boundary layer must decrease with increasing x, means when we move along the length, when we move in this direction along the length of the plate, so then the temperature gradients would decrease with increasing x, means that the temperature gradient at this x versus temperature gradient at this x. So as we go downstream, then the temperature gradients will decrease. See, the reason is that if we consider this location, this particular location, right? So at this particular location, the temperature varies from Ts to T infinity in this particular length, whereas if we are at this point, so at this x, T temperature varies from about Ts to T infinity in this length. So the temperature difference remains the same. So the temperature varies from Ts to infinity in a shorter length, whereas over here temperature varies from Ts to T infinity in a longer distance. So since the same temperature difference is being created in a longer distance, so therefore the temperature gradients of course would be smaller. The temperature differences of course would therefore be smaller. And then It further says that kindly note that we are talking about the temperature gradients in y direction. We are talking about the temperature gradients in y direction, because over here the value is Ts at this point, and the value of temperature is not greater than Ts at this point. Rather, it is temperature at Ts at this y, and then this y, and then at this y, and then at this y, and then at this y. So we are talking about the change in temperature at any particular x in y, at any particular x in y. So accordingly, the magnitude of dava t by dava y at y is equal to 0 decreases, of course, because when the temperature gradients are getting lesser and lesser, it means that the change of temperature in y would get lesser and lesser. It would decrease with increasing x. It would decrease as x increases, right, as we move along x. And therefore it follows that the heat or heat flux and h also decrease with increasing x. This is what is shown in this particular diagram. So what does it say? It says that when we move along the length of the plate, so the heat flux and h would decrease. See, why would it decrease? Because as we just discussed, that as we move along the length of the plate in x direction, the temperature gradients would become smaller and smaller. And if the temperature difference or the temperature gradients become smaller and smaller, then what will happen with the heat transfer? Of course, the heat transfer would get smaller and smaller. And what would happen with the h? Of course, if the heat transfer is getting smaller, then h will also decline, right? Because h is directly, because the heat transfer is directly proportional to h. So if we are observing a drop in Q, so that would certainly mean that there is a drop in h, keeping Ts minus T infinity as constant. So therefore, over here we can see that the boundary layer grows. Over here there is a laminar region, and then there is a transition region, and then there is fully turbulent region. So as you would know that the flow may be laminar, but when it is converted from when this transition from laminar to turbulent takes place, that particular region in between laminar and turbulent is termed as transition region. So over there in the laminar region we see an increase in the boundary layer, and then in the transition layer we show it in that manner due to the formation of eddies and all that, and then it again increases. So it again follows that particular trend which it was following in the laminar region, which was of an increase in the thickness of the thermal boundary layer. But when we look at the curve of h, see, this is the curve for delta. Delta x means the delta would change with x, and this is the curve for hx, means the change in x, change in h, change in the heat transfer coefficient with x in x direction. So as just discussed, there would be a decline in h. So while the fluid is flowing in the laminar region, h will continuously decline because of an increase in the boundary layer thickness, due to which would give rise to lesser temperature gradients, and those lesser temperature gradients would result in lesser Q, and lesser Q means lesser values of h. So the values of heat transfer convection coefficient will continuously decrease, and it will reach a certain value, and then the same trend will be followed in the turbulent region. In laminar flow, h was on a decline, and in the turbulent region you can see that h is still on a decline, right? While in the transition period it jumps to a higher value because of the transition from laminar to turbulent which takes place, and we know that in the heat transfer in case of turbulent flow is higher than the heat transfer in the laminar flow. So therefore, while the flow is in transition from laminar to turbulent, the heat transfer the value of the heat transfer coefficient will increase, because of the reason just explained. And then once the flow becomes fully turbulent, then the pattern of the decline in H will then be followed as it was being followed in the laminar region. So another important thing which you can see over here is that H is not constant, rather H varies along the length of the plate. H is not constant, rather it varies along the length of the plate. So therefore in a bit we would be talking about the local convective coefficient and average convective coefficient. So local coefficient would be the value of H at any particular x, whereas the average coefficient would be the average of all those values of H over the entire length of the plate. So we would be in a bit discussing about the local convection coefficient, which we call Hx. Hx means the value of H at any x, and that value would vary. And if we take the average of all those values of Hx, we call it average coefficient, and we denote it with an H bar. So therefore H bar is one average value of the convection coefficients over the entire surface, over the entire plate, and that average is calculated using the values of the local coefficients. Means H bar would be the average of the values of Hx. Okay. Now in the laminar and turbulent velocity boundary layers, there are some other layers that need discussion. In laminar flow, this is how the velocity profile looks like, and in laminar flow the streamlines are very smooth. But when we look at the turbulent flow, the streamlines are not that smooth, rather we see those eddies. The flow is rather chaotic, due to which the boundary layer would then consist of several layers within itself. And the first layer or first sublayer is what we call the viscous sublayer. And the viscous sublayer, as the name says, would be more streamlined. It would not be that chaotic. The flow will not be disturbed, will not be that disturbed as is over here in this region far from the plate. So and this will happen due to the viscosity of the fluid and due to the presence of the plate as well. But when we talk about, when we look into this region which is far from the plate, so the effects of the plate will also be minimized, will also be reduced, and in that particular region the flow would be more disturbed, it would be more chaotic, it would be less streamlined, and this particular region is what we call the turbulent region, and in between the viscous sublayer and the turbulent region there would be a buffer layer. So you can say buffer means something which is in between. So in between the viscous sublayer or what we also call the laminar sublayer and the turbulent region, there is a buffer layer, and you can see that this same phenomena is evident over here as well. While the flow is becoming turbulent from laminar, there is a transition region. Similarly, when the flow is becoming turbulent from this viscous or laminar sublayer, the transition region is being called as a buffer layer. Over here this length is called XC, and I was mentioning over here as well, this length is called XC. XC means critical length. Over here this is XC. XC refers to the critical length. Critical length is that length beyond which the flow will no more be laminar, rather transition will start and the flow will ultimately become fully turbulent. So this is the velocity boundary layer development on a flat plate when the flow becomes turbulent from completely laminar flow. These are the same things that I was mentioning over here. We have the viscous sublayer, which we also call laminar sublayer, and this is a very thin layer and very close to the wall, very close to the surface. It is very close to the surface of the wall, where the viscous effects are dominant. And that is why we call it viscous sublayer. And since it is relatively less chaotic, so that is why we call it laminar sublayer, because the streamlines are smooth. And then the velocity profile in this layer is nearly linear, and the flow is streamlined in that laminar sublayer. And then we have got this turbulent layer, in which the turbulent effects dominate, and we see that chaotic flow, formation of eddies over there. And in between the two we have got this buffer layer. You can go over this particular page yourself, but because we have discussed turbulent flow in a lot detail in the previous slides. However, you can see that before turbulence and after turbulence, what happens is that the molecules remain streamlined, 2 and 5 and then 7 and then 12. It is just for illustration purposes. However, when the turbulence takes place, the molecules get mingled up a lot due to that formation of eddies and the movement of the molecules, free movement of molecules, or rather unstreamlined movement of the molecules. So the molecules would start getting up mixed with each other a lot, of course, which results in more heat transfer, and that is why the turbulent heat transfer, the heat transfer in turbulent flow is more than the heat transfer in laminar flow, because the mixing gets increased a lot. It gets increased by many times, which gives rise to more heat transfer in the turbulent flow. Over here, let me explain the last expression very simply. It says that u is u bar plus u dash. So, for example, when we say that the velocity of the fluid is 10 meters per second, so every molecule will not be moving at 10 meters per second. Rather, there would be a little bit of difference in the individual velocities of the molecules. And what does this expression say is that the velocity would be equal to the average velocity plus a fluctuating component. Let me give you a very simple example. If a team scores 250 in 50 overs, so the average would be 5. But does that mean that they have scored 5 runs in each over? The answer is no. They would have scored different runs in different overs. So for example, if they score 3 runs in an over, so that 3 would be equal to 5. So that 3 would be equal to 5, means the average, plus a fluctuating component, and in this case the fluctuating component would be -2. So that 5 minus 2 would be equal to 3. However, if in any over they score, for example, 8 runs, so that 8 would be 5 plus the fluctuating component, in this case would be 3. So this is what is meant by this expression, that every value is equal to, or every molecule's value or the value at any particular location would be equal to the mean value plus a fluctuating component, and that fluctuating component may be positive or negative, right, depending upon the individual value. Over here we are seeing the same phenomena which we were discussing a while ago. You can see that when we have got a laminar flow, so in the case of laminar flow, change in velocity with y, or change in temperature in y is more, whereas in case of turbulent flow, this change becomes less, for the reason that I have explained on the previous slides. that when we move away, so when we come into the turbulent flow, there are more eddies and there is a lot mixing and it is not that streamlined. And you can see that over here they say dava u by dava y, but over here they say dava u bar over dava y. The reason is that again in the case of turbulent flow, we usually represent the velocities with an average value. And again that is the same thing, the same illustration, but I have taken this from Incorpora and Dewitt and this from Yunus Singhal, but they are telling us the same thing, that in case of laminar flow, changes in the velocities at any particular location would be less than in the case of turbulent region. Okay. Now we are going to discuss some of the dimensionless numbers, and we are starting from Reynolds number. Reynolds number should not be new for you. You would have already gone over Reynolds number in second year in fluid mechanics course. Reynolds number is in fact a ratio of the inertia forces to viscous forces, and we write it as rho v L over mu or rho v d over mu. L or LC represents the characteristic length, whereas in some cases characteristic length would be found out using volume over area or using some other methods. Now if Reynolds number is small, that shows that the viscous forces, that the inertia forces are less, and the fluid is flowing at lower velocity. So at small numbers, as you can see, the viscous forces are large enough to overcome the inertia forces and to keep the fluid in line. So the viscous forces, the highly viscous forces, would keep the flow very streamlined. The viscous forces will not let the flow get disturbed that easily. So therefore usually the small values of Reynolds number correspond to laminar flow, and high values of Reynolds number correspond to turbulent flow. Over here we also call it viscous diffusivity or momentum diffusivity, as the units are meter square per second if we work the units out for viscous forces, and same are the units for diffusivity. That is why we also call it viscous diffusivity or diffusivity for momentum. Now the critical Reynolds number is in fact 5 exponent 5 for the flow of fluid over a flat plate. It is important that for a fluid flow over flat plate, the critical Reynolds number is 5 exponent 5. So if the value of the Reynolds number is less than this value, we will determine that the flow is laminar, and if the calculated value of the Reynolds number is greater than this value, then the flow would be termed as turbulent, and it is V times, you can see over here, it is V times characteristic length, which we may call as X critical over the viscosity So this is the value for critical Reynolds number for flow over flat plates, but not for flow through pipes. We will discuss it when we will come on to that chapter where we would be discussing the flow through the pipes. That has already been covered, that lower values of Reynolds number usually correspond to the laminar flow, and we have discussed laminar flow in detail in the previous slides, whereas the higher values of Reynolds number usually correspond to turbulent flow, which are characterized by highly disordered motion. The next number that we would be discussing is Nusselt number. Nusselt number is a ratio of the heat transfer via convection to the heat transfer via conduction. And let's say we have got those two plates, and those two plates are being maintained at temperatures T1 and T2. Right? So if the fluid is still, if the fluid is not in motion, then the heat will be transferred from the higher temperature plate to the lower temperature plate via conduction, and that expression would be given as Ka delta T over delta X, or delta X may be written as length, where L is the thickness of the medium that the heat has to pass through. Now if the fluid starts moving, so then in the presence of bulk motion, the heat transfer will take place via convection, the expression of which will be given as Ha delta T. So if we divide that heat transferred via convection, if the fluid layer is in motion, to the heat transferred via conduction if the fluid layer is not in motion, in the absence of bulk fluid motion. So then upon cancelling the terms, of course this area and area will get cancelled out, and the temperature difference will also get cancelled out, and we will be left with HL over K. This ratio HL over K is called Nusselt number, but Nusselt number is in fact a ratio of the heat transfer via convection to the heat transfer via conduction. And we know that the heat transfer in case of convection would be more than the heat transfer in case of conduction. So therefore the convection heat transfer will be more than the conduction heat transfer in the due to the bulk fluid motion. However, if the larger the Nusselt number, of course, the more effective would be the convection. If Nusselt number is equal to 1, so that would mean that the heat transfer across those two bodies or across two layers is being transferred via pure conduction. If the convection heat transfer is more, then of course the Nusselt number would have a value greater than 1. So Nusselt number, it simply tells us the advantage or the effectiveness of convection over conduction. The next coefficient dimensionless number that we are going to discuss is Prandtl number. And Prandtl number is a ratio of the molecular momentum diffusivity to the thermal diffusivity. So the momentum diffusivity is what we represent with a nu, which we were discussing a couple of slides ago in Reynolds number. And the heat diffusivity is in fact represented with an alpha, and we had discussed the heat diffusivity for the very first time in the first chapter, where alpha was Q over rho c, and this momentum diffusivity or this kinematic viscosity is a ratio of the viscosity to the density. So the density will get cancelled out, and we will be left with mu times C over K. Mu times C over K. So this is the expression for Prandtl number. But Prandtl number is what is Prandtl number physically? It takes into account the relative thickness. It takes into account the relative thickness of the velocity boundary layer and the thermal boundary layer. This is what it takes into account. It takes into account the relative thickness of the velocity boundary layer. That is why we have this momentum diffusivity in the numerator, and the thermal boundary layer. So that is why we have this thermal diffusivity in the denominator. So the ratio of delta to delta T, the ratio of delta to delta t. Delta means the thickness of the momentum boundary layer, the velocity boundary layer. Sometimes we write it as delta, or sometimes we put a v in its suffix. So the ratio of delta to delta t. Delta t refers to the thickness of the thermal boundary layer. This particular ratio is called Prandtl number. See, the Prandtl number would be having values greater than 1 or less than 1 or equal to 1. Now if a Prandtl number, as you can see over here in the table, that Prandtl number for liquid metals is very small, right? And the Prandtl number for very viscous fluids such as oils and glycerine is very large. See, for the very obvious reason that the oils and the glycerine would have a very high viscosity, and therefore the momentum diffusivity would be much larger. So therefore the Prandtl number would have very high values. However, if we talk about liquid metals, so in that case the the thermal diffusivity would be very high, because they are metals, they are very good conductors of heat. So in the case of metals, for example, the thermal diffusivity would be much larger. So therefore the denominator would be having very large value, and therefore the value of the Prandtl number would be very small. So Prandtl number takes into account the momentum boundary layer and the thermal boundary layer. Over here we can see that if the Prandtl number is less than 1, then the thickness of the thermal boundary layer would be more than the thickness of the velocity boundary layer, because it is a ratio of delta to delta t. So if Prandtl number is less than 1, it means that the velocity boundary layer, it means that the numerator is less than the denominator. And what do we have in the numerator is the thickness of the velocity boundary layer. So the velocity boundary layer would have less thickness, and the thermal boundary layer would have more thickness if Prandtl number is less than 1. However, if Prandtl number is greater than 1, it means that the numerator would be greater than the denominator, and that would mean that the thickness of the velocity boundary layer at any particular x, at any particular location, would be more than the thickness of the thermal boundary layer. The next discussion is about local and average heat transfer coefficients. This is the same point that we were discussing a few slides ago, where there would be a local coefficient, since h would vary along the length of the plate. In fact, for laminar flow or if it is turbulent flow, then the value of h would decrease. So at every x there would be a different value of h, which we call the local value of the convection heat transfer coefficient. And if we take the average of all those values of hx, we call that the average convection heat transfer coefficient. So where hx is the value of the local heat transfer coefficient, and h bar, which is the average convection coefficient, would be obtained via this expression. Means if you integrate all the values of h over the entire surface, over the entire area, and if we then divide it by the total area, so then it would be average convection coefficient over the entire surface, over the complete surface. However, for the flow over a flat plate, h would vary only with the distance x from the leading edge. We were looking at that particular graph in which h was on a decline with an increase in x, with x. So in that case, h bar would be evaluated by integrating h over the entire length and not over the entire surface, because we would then be having h as a function of x. So therefore we would be integrating h with respect to x, and upon division of this summation, or rather integration, by the total length of the surface would give us the average convection coefficient over the entire length of the plate.